So we haven't had a question like this for a couple of years actually. So it's due to come up again. And I would, if I was predicting, I would predict that a question like this to do with fundamental theorem in terms of area will come up, or in terms of functions will come up, rather than use just straightforward fundamental theorem stuff that we did the other day. So here we have this scenario. You've got a graph. It's related to cos. It's a bit different, cos of x squared, and between 0 and 2. But what's important is being able to interpret what this represents. So every now and then in these questions you'll see over today, and then tomorrow you'll get, or next time I see you get a quiz. What does this mean? That a to the x. And when at that preamble today, I talked about that idea of, well, you've got this start point to some arbitrary value, x, whatever that might be. And so we're integrating from a start point 0 to some value. So if that value's here, I don't know, that looks like it might be about 0.6, then that integral is just the area under the curve. However, if that particular value is from 0 to 2, for example, then it's not the idea of the area under the curve, it's the idea of the integral, because you've got this bit that is going to give you a negative value, and so then that net effect will balance out to be, probably net effect will be slightly positive, but not as positive as it would normally be if that function was all above the x-axis. And so you need to think about that in terms of questions coming up. So let's have a look. Determine the value of x when a of x starts to decrease. So I think I've just given that away, haven't I?
How do we know that a of x is related to cos x squared?
Because of the f of t dt. So when you add, so that's function f, and there's your function f. Oh, okay. So it's that's got to be the same. Yeah, good question. So when does it start to decrease? Well, I think I've just answered that, didn't I? Yeah, this value here. Because up until that point, that area under the curve will get bigger and bigger and bigger. And then because, remember, the integral is not just about area, because then this starts to become negative under here, that is the highest value it will be within that domain at least. And so what is that value? Do we need to know it exactly? For 3 marks, yes. This is a Calc Aloud question. It is question 20. So really, what are we actually solving here? Yeah, cos x squared equal to 0. And you can do that on your calculator. I think I'm getting 1.253. If we were asked to do this exactly, how do we do it? Actually, it might work in standard mode on the calculator, but really you're solving cos equal to 0 first. And if cos equals 0, when is cos equal to 0? Sorry, that's going to be at pi on 2. Yeah. Well, that's the first one, and then you've got the rest. Obviously, goes on and on forever. Within that domain, though, it will be less. And so, and there's only one solution. X is going to be plus or minus the square root of pi on 2, but in this case, we reject the negative because clearly x is a positive solution here. Okay, we're not interested in what's going on below 0. So if we did that without a calculator, that's how we would approach it. All right, so it does say complete the table below, so I'll give you a chance to do that. And again, remember, this is Calc Aloud. So we do this by using that box in red, 0 to x. So we start from 0 to, the first value is 0.6, but that you're missing, but I'll just show you at 0.2, the function is cos x squared. And that should be 0.2. Well, it is to 3 decimal places at least. So we are doing this from 0 to 0.6 for the first one. So 0.592. And basically we keep going. So change to 1.4. Whoops. So 0.950. And I'll let you finish that off. So the maximum of graph C occurs at this point because it gets bigger and bigger and bigger all the way up to this point, and then it starts to decrease. However, it is not a quadratic. But it should make sense to you that if you were to graph the derivative of this function, the point is you get back to that. Yeah, the derivative of the integral is the same. So that key point is that 0 value, and then it kind of decreases, but not linearly. And I don't know, however it works between 0 and 2, that's what the original function looked like. And I suppose if we want to be exact, that's 1. And the point is to say that a dash x is just cos of x squared, which is what we started with in the first place. And that's the point. That's just trying to give you a bit of an understanding of how this works. And it is certainly a lot easier to go from the function to the derivative. It's a lot harder to go from the derivative to the function. And I guess that's what this is trying to say. Think of this, so there's a couple of ways to treat this, but one way is to treat this as the derivative function, because we've got to anti-differentiate, and we've got to end up with this, which can be determined just by a table of values like that. So it's much easier to start from the orange graph and go to the purple rather than the other way around. But that's another way of thinking about it. All right, so that's that question. So here's another one. Similar kind of idea, I'll let you have a go. All right, how are we going with this one? So if we think about, we're starting at -4. So if we think about what's going on from -4 to whatever value, that area is going to get bigger and bigger up to that -2 value. So that's going to give you a local maximum. And then the integral value, which is the area if it's all above the x-axis. Remember, now the graph is below the x-axis. So if we keep going, this looks like almost symmetrical there. And so then if we keep going again, this is going to give you a negative value. So that's going to give you a minimum, a local minimum. And then if we keep going, assuming there's symmetry, which we can't guarantee, by the time we get to that point, the net effect of everything, area above, area below, is going to be pretty close to 0. We can't guarantee that that's symmetrical unless we know the function itself. But it looks pretty symmetrical in terms of those 4 different area shaded parts that I've shaded there. So most likely the net effect of that is going to be 0. 2 areas above, 2 below. Cancel each other out. Whoops. But in terms of answering part A, what's happened to my graph? In terms of answering part A, you've got to identify where these maximum and minimums are going to be. So at x equals -2, that's going to give you a max, because that'll give you the maximum possible area up to that point. Then it's going to start to decrease until we get to this point where x equals 2 is going to give you a minimum. Up to that point, net effect is 0. Then it's just going to keep getting bigger and bigger and bigger all the way along. Why is knowing a of 4 is 0 helpful? Yeah, so the purple and the red must match the orange, basically. So that's very helpful for us if we keep then going on, because now this is pretty straight. So we can start looking at rectangles, a rectangle there if we need to get further along. And I think that's actually what the question in part B is asking. So using the graph, explain why a of 7 is equal to 6. So net effect up to this point is 0. why is that equal to 6? Well, this area in green is just, 3 times 2. So that's why that's 6. So we could do that more formally, but really that's all that's needed. That 3 times 2 is 6. So it's that integral from 4 to 7. And then you know the integral from -4 to 4, we know that's 0. So it's just that bit, that's 6. So when we start drawing this, we know that a of -4 is 0. That's your start point, so that's always going to be there. And then we know there's a maximum at -2. We know that there's a root here and an inflection point because we're making the assumption that this area here, because the net effect is 0 from -4 to 4, that this and this are the same, which is pretty safe bet and then we're going to make the assumption that that and that are the same. So because this is a maximum point of steepness, at that point, that's going to be the inflection point in the actual integral function. So it's going to go up to some maximum value, which we don't know for sure. It's going to come down and at that point, and then it's going to reach a minimum value at -2. At 2. And then, so that's a bit ambiguous, not knowing, because we don't know the function, those exact points. So that's not important. It's just important to show that you've got a maximum here, you've got a minimum here. So that's when x equals 2, and that's when x equals -2. It does say label. So if you don't label, you will lose marks. So be very careful with that. And then we know that this one here, that's your root because we're told that a of 4 is 0. So that's pretty handy. And now the next bit we can actually calculate because that's just your rectangle. So that should be a nice straight line. We know that up here we've got a of 7 is 6. So there's one point we can plot. And then we're going to have a nice straight line through there, basically. Now you can try a couple of other points if you like. Use a ruler, don't do what I'm doing, but that should be, using a ruler, that should be a straight line. Which should make sense to you, because if you start with a constant, when we aim to differentiate, that's going to take you, or think of it the other way. If you've got a line like this, the derivative of that is flat at 0. So we're going back the other way now. A lot harder to do it that way than start with this and go to the other one. So with this one, trapezium, or you could split it up into a rectangle and a triangle. So your A and B values are just the two parallel sides, and then the height is that there. So that's for your trapezium. And then here we have that idea of y equals capital F of x, and capital F is from 0 to x, etc. So really it's just a matter of finding some values. So we've got that first one already down pat for you. That's f of 2. So we know f of 2 is 7. There's 1 point. 2, 4, 6, 8. So f of 2 is 7. And then if we keep going, we can do a few more. F of 3, or actually f of 4, it's probably a bit easier. So using that trapezium idea, we get 12. So this trapezium, so using this trapezium, that one.
Oh, okay. Okay,
That's okay. And then at 6, a bit more. So this time the height of the trapezium at 6 is 6, I think. So I haven't done a very good job here. My scale is not good. I'm going to change it because otherwise I'm not going to fit the graph. So I think I'm going to go up in 2s, I think. So let's try that again. 2 to 8. No, 2 to 7, I should say. F of 4 is 12. F of 6 is 15. And then F of 8, if we keep going, is 16. What can you tell me about F of 8? Yeah, that's the maximum here. And then it starts to go down again. So F of 10, what's that? Well, let's take that little triangle part away. That area is just 1, yeah? So F of 10 is 15. All right, so that's kind of what we're looking at in terms of our graph. Make sure we show that maximum. And really, that's the understanding that we need with this kind of thing. So don't be scared when you see this. Look out for it, because sometimes it comes up in the most unusual places. I've seen this come up in an optimization question. I'm going to give you that in the quiz coming up tomorrow or next time I see you. So just look out for that because it does come up. But just think logically about what that represents in terms of how we just keep increasing this area until the function ends up being below the x-axis and then that value starts to decrease. And the other way you can think of it is what we're drawing here is the antiderivative of this function up here.